Now we're going to continue talking about probability. We're going to start with unions and intersections. Here we're going to look at the probability of rolling a number that's even and divisible by 3, even or divisible by 3 on a single roll of a fair die. Our keywords and or should make you think of unions and intersections. Let's define some sets. Let's let E be the set of even numbers that are possible when we roll a die. And so then my E would be equal to what? 2, 4, 6. Let's let T be the set of numbers divisible by 3. And so then my T would be 3, 6. Getting our sets defined lets us clearly say what probabilities we're talking about. Our sample space is equally likely, so our sample space, of course, will be the numbers 1, 2, 3, 4, 5, 6. So the probability that a number is even and also divisible by 3, so this will be for part A. That's our intersection. Okay, now let's figure out what our intersection is. What numbers are in both E and also T? Looks like just 6. And so what's that probability? 1/6. Now let's find the probability that we roll a number that's even or divisible by 3. So let's once again write down the set that we are talking about. So it's got to contain everything in E and also everything that's in T. So that'll be 2, 4, 6. Now come over to T. 6 is already in there, but 3 needs to be added. So we have 4 elements in our set. So what's the probability of that? 4 out of 6, or 2/3. So often we can figure out the probabilities of unions and intersections simply by examining the events in a simple problem like this. It does turn out, though, that it is sometimes helpful to look at a formula. This formula should look familiar to you. This is not a new concept. Remember our counting formula that said that the number of elements in A union B, what was it equal to? Well, it was equal to the number in A plus the number in B, and then we had to subtract the ones that were the intersection because they had been included in both, so they'd been counted twice. Works for probabilities also. Hang on, we should have a plus sign in here. And the second one, the probability, if they're mutually exclusive, that should be equal. The probability of the union is equal to the probability of A plus the probability of B. And so if we go back to our previous example and we use that, let's go back. Okay, here's another approach. So the probability of E is 3/6. The probability of T is 2/6. You could reduce these, but I've left them because it's easier to combine fractions if they already have common denominators. Okay, the probability of the intersection we already decided was 1/6. And so now if we look, the probability of E union T is equal to the probability of E plus the probability of T minus the probability of the intersection. So 3/6 plus 2/6 minus 1/6 gives me 5/6 minus 1/6, so 4/6, which is 2/3. thirds. Same answer. I'm not saying that's the most efficient way to do it. I think probably the best way to do it is the way that we did it the first time, just examining the union. But it's good to verify the formula and see that it makes sense. Okay, let's suppose that we have a sample space described by a Venn diagram, and we're going to suppose that the sample space is equally likely. Drawing a Venn diagram like this is often very helpful in solving probability problems. So we want to figure out the probability of A union B. All we need to do is figure out where the union is. Where's our union? Everything in here and also here, right? That's our union. So what's my probability? Well, how many are in the union? 15 plus 10 plus 30. Now how many are in the total sample space? Well, 45 plus 15 plus 10 plus 30. And you could have figured these out beforehand before you put them in there if you wanted. And so this will be 25 plus 30, that's 55 over 55, 45, 100. So 55 over 100, or 0.55. And you could also do this with the addition formula above. Now let's look at complements. The probability of a complement is equal to 1 minus the probability of the event. Okay? Remember, when you have two events that are complements of one another, it can be arranged either way. Probability of E complement is equal to 1 minus P of E, or since E is the complement of E complement, then we get the second version of this concept. It's written as a formula, but really it's more of a concept. Just the idea of the total probabilities having to add up to 1. Let's suppose that the probability of someone voting for a certain candidate is 0.46. What's the probability of not voting for the candidate? Okay. So the probability of the event is 0.46, and so the probability then of the complement is going to be 1 minus 0.46, which is 0.54. Okay, let's move on. Suppose we roll a pair of dice. What's the probability of rolling a sum of 4 or more? Okay, first we need to remember what our sample space is. I'm not going to write the whole thing down, but we've seen it before. Remember all our ordered pairs? 1, 1, 1, 2, 1, 3. And then we can keep going. 2, 1, 2, 2. Hang on. Teach me to write them all down separately. Okay, so let's do, this will be up to 6, 1, and then 6, 2, 6, 6, like that. Okay, so remember how many are in here? 36, right? Okay, so we've seen that sample space before. We want to figure out the probability that we roll a sum of 4 or more. So we'll call that event E. Okay, and so then if we write down all the outcomes that are in this event, that means that's going to be a lot of outcomes to write, isn't it? If the sum is 4 or more, so what could our sum be then? 4, 5, 6, 7, 8, 9, 10, 11, 12. I don't want to write down all the ordered pairs for all of those because I'm going to end up writing nearly the entire sample space. So I'm not going to do that. I'm going to want to use the complement instead. Okay, so let's write down E complement. Okay, and let's write it down in words first. So, if the sum is not 4 or more, what is it? Well, that means it's going to be less than 4, right? Okay, if it's less than 4, what's the smallest sum we can have? 2. So 2 or 3. Those are the only possible sums that are going to be less than 4. And so if I actually write down this event, the ordered pair 1, 1 will give me a sum of 2. To get a sum of 3, I'll need 1, 2, or 2, 1. So what is the probability of E complement then? 3 out of 36, or 1/12. So now we can use that to find the probability of E. Okay, so this is going to be 1 minus 3 over 36. So do your common denominators. So we end up with 11/12. Really, common denominators is fine and all, but we can just think about if we have about the number of items that are in the complement. If we have 36 in the sample space and 3 of them are in the complement, how many of them have to be in the event? Well, the other 33. Therefore, we get 33 over 36. And so we could almost jump right there. So you always want to figure out what's easier, the event or the complement. If you can find the probability of the complement, it's very easy to find the probability of the event. We just subtract from 1. Okay, I hope this helped you to learn about unions, intersections, complements, and how they relate to probabilities. Good luck, and we'll see you next time.